the last model for this week. It's called the predator-prey model. That's a model describing the existence of a prey and the existence of a predator. The idea is that the prey is going to be eaten by the predator. So the prey has a term that is minus alpha y times x that indicates how x is dying because y is eating on it. And then there is a term in y that indicates how y is living because it's eating x. This is term gamma xy. The problem is that if the predator eats too much prey, then the predator is not able to find any prey anymore. So if the prey goes extinct, the predator goes extinct. While if the prey is having a really good time and there is a lot of prey, then the predator is going to eat a lot and procreate a lot and grow as well. So there is this balancing effect between prey growing, predator growing, prey decreasing, predator decreasing. It's called the Lotka-Volterra equation. Let's look at an example. We have x prime equals x times 1 minus 2y, and y prime is equal to y times minus 2 plus x. As before, we can compute the null lines. We retrieve that the null lines for x prime equal to 0 are x equal to 0 and y equals 1/2, and the null lines associated to y prime equal to 0 are y equal to 0 and x equal to 2. So we have this boxes. On the green lines, x prime is equal to 0, so we're moving only vertically. On the red lines, y prime is equal to 0, so we're only moving horizontally. At the crossing between the red lines and the blue lines, we find the equilibrium. We find an equilibrium at 0, 0, and an equilibrium at 2, 1/2. That means that if you start at 0, 0, nothing is going to grow. If you start at 2, 1/2, the equilibrium is going to get kept. And we have this behavior of horizontal behavior at the red lines, vertical behavior at the green lines. Then we can compute the stability of the equilibrium. So we compute the Jacobian, that is minus 1 minus 2y minus 2x, y minus 2 plus x. And we compute it at 0, 1. That gives 0, 0, sorry. That gives us a Jacobian that is 1, 0, 0 minus 2, associated with the eigenpairs 1, 1, 0, and minus 2, 0, 1. So the equilibrium is a saddle node. That's interesting because it means that if you are moving towards the equilibrium, you're going to be bounced off. So it's a saddle node. In the vertical direction, you're moving towards it. In the horizontal direction, you're moving away from it. And everything that is not exactly on the vertical direction is moving through it. And let's look at the other equilibrium. We only have two. So at 2, 1/2, we have a Jacobian that is 0 minus 4, 1/2, 0. That is associated with the eigenvalues plus or minus imaginary number times square root of 2. These eigenvalues are purely imaginary. This is the case in which linear approximation is not enough. So we know that 2, 1/2 is a linear center, but that is not enough to know that the nonlinear problem has a given stability. It's enough to say that the nonlinear problem has oscillations, so we are spiraling around it, but we don't know if we're spiraling towards it, away from it, or we actually are closing our circles back. In order to have more information about it, we need to find another way to approach this problem. So our information is like this. We know that at 0, 0 we have a saddle node, and we know there is some turning around on the other equilibrium. Stability still unknown. Is it a stable saddle that is moving towards it, away from it, a circle? All are options. A squiggly circle. It's nonlinear after all. So we have to find another method. We use the method of ratios between dx and dy. So we write dy over dx as the ratio between dy over dt and dx over dt. That means, coming from our equation, we have y x minus 2 divided x times y minus 1 minus 2y. We can move things around, and we have 1 minus 2y divided by y times dy equals x minus 2 divided by x times dx. This gives us, if we integrate both sides, that the logarithm of y minus 2y is equal to x minus twice the logarithm of x plus some constant. So now what we're interested in is the contour plot of the function logarithm of y minus 2y plus, minus x plus 2 logarithm of x. It actually turns out that when you plot the contour plot of this, you retrieve some circle-like behavior. So the trajectories close back on themselves. That means that in the predator-prey model, our second equilibrium is a non-linear center. Not only a linear center, as we found for the linear approximation, but also a non-linear center. So now that we have information about both of them, and we also have information, actually explicit information about all the trajectories, we can make a drawing about them. Every single line that you see here, except the vertical line and the horizontal line, all the other curves sooner or later close back on themselves. That means that in this predator-prey model, it actually is true for all parameters of the predator-prey model. The non-zero equilibrium is a nonlinear center, and everything behaves, doesn't matter where you start in your phase plane, you're going to come back to it at some point. We call that a periodic orbit.